So once we've completed the design of our accessible bathroom, we're going to be adding some plumbing systems to it. And so in order to prepare for that, we're going to talk a little bit about, in this module, the one that we're also working on, the accessibility issues, we're going to talk about that idea of fresh water and the quality of water. And then the next module will pick up on the idea of what to do with wastewater. But drinking water, an important piece of subject matter for architects. We many times we're responsible parties for making sure that we have clean drinking water available for the sites that we develop. Many times we take that for granted and can take it for granted in urban settings. But there are rural settings. There are other countries that we work in where access to clean drinking water is not assured. But for the most of our discussions, we're going to, in this presentation at least, look at this idea of having a good, a source of drinkable, potable water, as it is referred to, potable. And we use it in our systems in many different ways, and that's another aspect of us to be aware of that. Um, it's very common for us to understand that we use it for drinking and cooking, but we also may be involved in the site development that uses it for other issues like industrial processes and irrigation. And then this idea of the clarity of the water, the quality of the water can become a little more complex and nuanced. And when I say that, I'm kind of reaching towards this next slide here, this idea of gray water. The vegetation around the site may be irrigated with water that comes from sinks, certain kinds of industrial washing processes, things that leave the water not fit for drinking, no longer potable, but still very available for irrigation and other uses, secondary uses. And that contaminated water, not unhealthy contaminants, but contaminants that no longer make it suitable for drinking, leave us referring to it as gray water. So we've introduced that idea of gray water and its potential uses, but so we really divide things into those two kind of categories: water quality, and then this idea of potential contaminants. And like I said, some of those contaminants can be relatively innocuous, and other ones can be seriously hazardous. So we always want to pay a lot of attention to this idea of what's in the water that we are providing for whatever application. So this idea of water contaminants, a lot of our water in our region comes from the Great Lakes. In other places, it comes from wells and reservoirs. And all of those are subject to inherent natural pollutions. And I say natural, but man-made pollutions in the natural environment. So here we have just some idea of this, of those kind of contaminants. So we have these VOCs, which are referred to as volatile organic compounds, plus sulfur dioxide, nitrous oxide, and they become airborne, and then can come down as particulates, either condensed in rainfall or just dust blowing onto the leaves and greenery, and then absorbed into the soil, and can then repass into groundwater sources, and or flush back into our lakes where we may be taking water for drinking. So most of our water that we take for drinking needs pre-treatment to remove these and other contaminants that happen to them. In a bigger picture, there's this idea of acid rain, and that's really the change of the acidity of the rain because of these kind of factory gases that are given off. And many times this is, when we talk about this gas, it's really just a byproduct of combustion, of burning natural gas and coals. So one of the ways we look at the problem with that idea of acidity is we need our water to be in a relatively neutral range to make it potable, drinkable, and useful for things like irrigation and cleaning and all kinds of other purposes. So this idea of acidity can be measured, and the term that we use is pH. This would become something that an architect would discuss, um, not in common practice with city water, but if you were working in rural property and digging a well, the issue of the alkalinity or acidity of the water would become an issue, and a discussion about needing to treat that water in order to neutralize the pH of it to make it more drinkable, so to speak. So that, in this case, that contaminant is not necessarily a toxic or harmful contaminant, but it is one that affects the qualities of the water, its taste, its ability to clean as far as lather and soap, um, and cause corrosion. So here we have this idea of water hardness, of minerals deposited within the water, both affecting its alkalinity and its hardness. So we have things like limestone, calcium, and magnesium. And this is not a winter scene of water. This is a mineral-rich water source, and these are the um, condensates, the crystalline forms from water evaporating out and leaving just the minerals in its wake. And this is also seen in our plumbing systems. So here we have, once again, these hardness or these water contaminants aren't harmful to humans. They actually could be beneficial. But they do have issues about, as I've said, the ability to lather. Hard water is very difficult to lather and clean with, and it leaves deposits on our plumbing systems. So in this case, we're looking at cross sections of pipes, and we're looking at the growth of minerals and other sediments within inside of the pipe, corrosions. And the negative effect here, and the one that an architect would be concerned with in the long term, is that the pipes become so full of mineral scales on the inside that they can no longer pass fluids, the water, and we need to repair the plumbing. The alternate to this, though, could be as an architect to specifying materials in your plumbing systems that don't allow minerals to adhere to them as readily. And I'm really not prepared to kind of like delineate which ones would be better or worse, but that would be a subject for research if you were presented with water that was unusually hard. So there are ways to treat these contaminants, these less noxious contaminants, um, and that's called water softeners. They're called ion replacement water softeners. They're filled with salts that then change the pH and hardness of the water to make it more usable. This unit that I'm showing you on the right-hand side is a large-scale unit that would process all of the water in a household. And then we have this on the left side, a, um, a much simpler water processing that deals with filtering the water for just specifically for drinking. This can be in places where the water quality is not is still potable, but maybe of not the quality that the your customer, your client, or yourself may be happy with as far as for food preparation. And in this case, they tap into the supply line. They can filter it with activated carbon and put it through a host of filters. So we have 321. These are just three filter canisters, one with, it looks like more activated carbon in it, a reverse osmosis membrane housing, which is a very high quality filtering system. And it looks like a pre-carbon filter housing. So what's probably happening here is the first one roughly filters the water. Number two very carefully filters fine particulate out, very fine. And then the third one is post-processing. And then it looks like it's probably stored over here. One of the reasons why we would have a storage container alongside is that this reverse osmosis filter is very slow as far as the amount of fluid that can move through it. And that's because it's so fine, it restricts a lot of particulate. So we've looked at now this idea of in-house treatment of water in order to make it useful to us. And this is really the place where we as architects would deal with it. We'd have to accommodate the equipment in the spaces that we're designing. and be sensitive to the idea that we have problematic water that might need this kind of treatment, so as to prepare our design briefs for the kitchens, the processing areas that we create. But on the larger picture, that same kind of water treatment happens on a big scale. Um, in Western New York, we have a relatively very clean source of water with the Great Lakes, and we have some of the best quality of water in the state. But in this, we're going through the same idea of treatment of water. So we have raw water coming in. In this case, it's not a canal; it's the lake. Um, Always this idea of activated carbon to create, um, first of all, some reactions with the carbon to filter some of the active biologicals in it. And then it's passed to a tank system where sediments can settle out of it. It's filtered. Fluorine is added, a very small quantity of it, but a very strong tool to kill any biological activity within the water system. And then one of the other things that most people don't think about any longer is this addition of fluoride. And the fluoride is added in, takes very little in parts per million, but it's been associated with a positive benefit and in our dental hardness. Fluorides react with our enamel and make our enamel very strong. Really important for young children. So it's been a standard in most municipal water supplies. And it's another thing to consider when we talk about this idea of using well water that isn't treated with fluoride, that the occupants, that if it's residents, they need to realize that no fluoride treatment is available and that the toothpaste that we use or that they use should contain that fluoride so that they get adequate protection for their teeth. So we've covered kind of the noxious or the not harmful contaminants in our water, but there are all kinds of other ones besides this idea of the contaminants that come over from fossil fuel burning that have been in our society for a long time or in our built environment. Um, and a few of these that you should be aware of are PCBs. They are a fluid that was used in transformers as a cooling fluid. It was, and I don't know what what the actual chemical is here, but it's considered a known carcinogen. And in older transformers, it can leak out and contaminate groundwater. It was banned in 1979, but it still exists in the environment. DDTs are still used, but they're much more controlled. But they were affecting groundwater. One of the biggest negative effects of DDT was in the inability of bird nesting eggs to form hardness to them, causing major disruptions in our natural ecological systems. Asbestos, a fibrous material, a known carcinogen, lung cancer. And now we have a new one, fracking chemicals, the chemicals that are introduced into the water that's driven into the ground to break up rock to allow natural gas to come out. So one of the fracking is a contemporary way of extracting large quantities of natural gas. That's why natural gas today is very cheap. But one of the negatives of that are the chemicals that are placed into our water. And in some cases, some states have banned the use of fracking because of the introduction of chemicals. Because when we introduce this water into our ground, it also contaminates our groundwater. So something to think about when we're talking about developing well systems or other drinking systems for clients in rural areas. And then we have this idea of organics that can get into our water systems. Like I said, with municipal systems, it's really not much of a concern. Specifically, there can be errors in our plumbing systems that can introduce this, but for the most part, we don't have a concern with this. But human and animal waste and organic decays, any biologicals that can get into our water source can either be in and of themselves harmful or host other harmful biologicals that can make us sick, like E. coli. So that really kind of wraps up this idea of what we need to know, or at least be thinking about when we're thinking about fresh water supply for the projects that we're working on.